All right, where are we at? Last time, we started off with talking about graph theory. And today, we are talking about more graph theory. How good. So in particular, we'll be talking about a few ways of modifying graphs, and then talking about isomorphisms of graphs. So let's start off with talking about subgraphs. So what is a subgraph? It is hopefully more or less what it sounds like. So a subgraph of a graph G, which is a set of vertices and a set of edges, is a graph H, which has its own set of vertices and its own set of edges. And these should be subsets of the set of vertices of G and of the set of edges of G. So it's just another graph that you get by taking some subset of the vertices and some subset of the edges. And it is called proper if it is not the whole graph. So let's look at an example. So here is a graph. And let me make a quick note that when I say a subset of the vertices and a subset of edges, of course, you can't take just any subset because it has to form a graph. So for example, you can't choose an edge to be in your subgraph unless both of the vertices that form its endpoints are also in your subgraph. But with that obvious caveat, you can do basically anything you want. So an example of a subgraph of this thing is we can take these three vertices and those two edges. So this part of it, that's a subgraph. And we can take a subgraph of this thing, which maybe just consists of these two vertices. Good. And that's basic enough. Let's give a couple of basic facts about subgraphs, or like things that we can say about subgraphs or do with subgraphs. So one fact is that every graph is a subgraph of a complete graph. And this is just because, if your graph has n vertices, you can just take the complete graph on n vertices, and that has all the edges that you could possibly have. So you can always get your original graph by deleting some of the edges. So for example, this guy we started with up here, we could have taken the complete graph on 4 vertices, and we could take the subgraph that just leaves out this one edge. So that gives us our guy that we started with up there. And you can do this for any graph just by taking the complete graph with the same number of vertices and deleting some of the edges. Another thing we can say, a nice little fact about bipartite graphs. So, or a nice little criterion for checking that a graph is or is not bipartite. If the graph contains a triangle as a subgraph, then it is not bipartite. So this is not if only if. You can, certainly there are graphs that are not bipartite that also do not contain triangle subgraphs. But we do get the one direction that if you contain a triangle as a subgraph, then you're not bipartite. And that's essentially because you can just consider which side of the partition each of these vertices can lie on. And basically, you can't separate these three vertices already into two different sets in a bipartite way. So any graph containing this, you will not be able to separate that either. In fact, that is a nice exercise that I think I made a practice problem to show that every subgraph of a bipartite graph is, again, bipartite. So that's a nice example of problems or properties that you can check, or that it's helpful to check when you're looking at subgraphs. A closely related definition, if we have a graph G with its set of vertices and set of edges, and we take a subset of the vertex set, then we can consider the induced subgraph maybe I'll say on W is the subgraph that we get by taking W for the set of vertices and the set of edges is equal to all edges connecting two vertices in W. So a subgraph is some subset of vertices and some subset of edges. It is an induced subgraph if it has all of the possible edges that you could get on those vertices from the original graph. So in the example that we were doing before, for this graph, and this subgraph that we wrote down, so this is a subgraph. In fact, it is the induced subgraph on these three vertices of our graph. Because if we take these three vertices, what are all the edges of this graph that we can draw between them? Well, it's just this edge and this edge. And that is what is happening in our subgraph. On the other hand, so something like this is also a subgraph, but it is not an induced subgraph. The induced subgraph on these vertices, so if we consider these three vertices and look at all the edges connecting them, we should get this whole part of the graph. So the induced subgraph on these vertices looks like that. And there's a nice fact about induced subgraphs that relates back to something we've shown before. Every graph with at least 6 vertices has an induced subgraph of the form triangle, or 3 disconnected vertices. And you may recognize this as, so this is just a way to rephrase Ramsey's theorem, basically that R33 equals 6. So this is, in this language, just a way of restating the fact that if you have 6 people in a room, you always have a group of 3 mutual friends or 3 mutual strangers. In the language of graphs, that's saying if you have a graph with at least 6 vertices, then you have either 3 vertices that are all connected to each other, which forms this induced subgraph, or 3 vertices, none of which are connected to each other, which forms this induced subgraph.